Hi everyone! In this video, you can see in front of me I have several devices, which are the result of this last week's worth of experimentation. These devices are meant for electrolysis, which is the electrochemical process of splitting water into its component atomic parts, hydrogen and oxygen. And I have attempted to develop these models for electrolysis independently of other designs because I wanted to be original in my thinking and hopefully have something new to contribute. So this is the first electrolysis design I came up with for this video, and there are a few features that I really like that I continue to use in my following designs. So we'll go over those first. For my electrodes, I am using a stainless steel whisk, like this one. These are less than $1 at Walmart, and there are some features of this that are very good for electrolysis. First of all, they are made of stainless steel, and in order to generate hydrogen and oxygen gas through electrolysis, you need a metal that will not easily corrode when you pass electricity through it. These in particular are also great because they are adjustable. Simply by sliding the spacer down over the wires, you get a much smaller electrode, and you can slide this metal sleeve down to hold it in place. Now this will fit in a much smaller container or a large one if you slide it back up. What's also interesting about using these as an electrode is that this metal tube is not completely filled by the volume of the wires that pass through it, leaving enough room for gas to flow through this tube, which means when used as the electrode in an electrolysis setup, this can double both as the electrode and the gas outlet. In this design, if I simply attach a tube over the end of the whisk and down over the metal sleeve, now I have a tube which can act as my gas outlet, and I only had to drill one hole through the lid in order to accomplish this. Both the electrode and the gas output are one and the same. These whisks also work really well as electrodes because it's really easy to increase their surface area to increase the efficiency of the electrolysis process. And the best way to do this is with a stainless steel scouring pad. These are made of very fine stainless steel turnings, and these pads can easily be inserted into the wires of the whisk, greatly increasing the surface area where the water will be able to react with the electricity that we pass through these electrodes, separating them more efficiently into oxygen and hydrogen. Now, in this particular setup, I have one whisk inserted into each bottle. So we have two separate electrodes in two separate containers, which allows us to produce oxygen and hydrogen gas in a separate outlet. So in order to start generating these gases, what I do is I will connect up the wires from my power supply onto each of my electrodes and turn on the power. Now, right now, this power supply is at maximum capacity at 31 volts, and this system at that voltage is only drawing about 0.12 amps, which is very bad. We should see a much higher current draw at that voltage, and, well, that's due to some flaws in this system. First of all, these bottles are electrically connected to one another through this tube right here. This is a siphon bridge where I have the end of this tube submerged in the liquid in each of these bottles and then filled with the liquid itself. So electricity can pass from one bottle to the other through this liquid. Now, these bottles are filled with plain ordinary water, and to increase the electrical conductivity, you need to add an electrolyte. In this case, I have used potassium hydroxide, which is one of the best electrolytes for electrolysis. It greatly increases the electrical conductivity of water and also aids in the generation of particularly hydrogen gas. However, since this electrical connection is so greatly divided, we barely see any bubbles forming on our electrodes. In an ideal setup, the electrodes should be as close together as possible so electricity can easily pass between them. In this case, electricity has to go all the way up through this siphon bridge and down to reach the other container. This is my version 2 electrolysis setup. This is very similar to the first one we looked at. We still have two separate bottles, but in this case they are both contained inside a larger bottle which will hold a reservoir of fluid. There's no siphon bridge between the two, and so the electricity can flow between these bottles much more easily because the bottom is cut off, which allows electricity to pass only a very short distance between the bottom of each bottle instead of traveling all the way up and around almost 12 inches to make electrical contact in my first design. Because of that, this version works significantly better at producing gas. The only problem is that this setup has an open top, which means it's very easy to tip over and spill. If I were to fill this setup with water and then a solution of lye or potassium hydroxide, we would have a very dangerous situation on our hands where this container could easily tip over and spill a hot, caustic solution all over me. I'm forced to use an inferior electrolyte, in this case, baking soda. Now, potassium hydroxide is approximately 3 times more efficient at producing hydrogen and oxygen gas through electrolysis, but still we'll see what we can do. When I add this electrolyte to the system, we should see the amperage rise rapidly, and hopefully we will be able to start some gas production. Let's give it a shot. Now, I am starting to see some significant gas production in this setup, and we are pulling almost 1.7 amps at 31 volts, which is more than 10 times more effective than our first setup. Now, because we used the baking soda as the electrolyte, this result could be more than 3 times better if we were using potassium hydroxide. But unfortunately, because of the open top to this design, it's just too dangerous to use that corrosive of a solution. So the baking soda is the limiting factor. If we close this system so that we can use the better electrolyte of potassium hydroxide, we should see an even better result. And here it is, the final version of my split output electrolysis device using the stainless steel whisk electrodes. And in this case, it is packed into a single watertight container so I can feel safe using potassium hydroxide as the electrolyte. Now, in order to construct this, it was a simple process of drilling 2 holes straight through the lid of this container so that the stainless steel tube that surrounds the handle of the whisk could pass through the lid and then through the cap of several bottle caps on the underside. Now, the reason for these bottles, as with the previous version, is to direct the gas bubbles upwards that are formed around each electrode. So hydrogen only flows upward and out of this tube and oxygen out of this one, if I have it connected in that configuration. We'll take this lid back off and load this container up with electrolyte and then connect the power supply and see what happens. Now, in this case, I am so confident that this is going to work extremely well that before I turn on this power supply, I'm going to turn the voltage way down because we're not going to need nearly as many volts to reach a high current using potassium hydroxide. So I've got this connected up so that we're producing hydrogen out of this side, oxygen out of this side. Let me turn on the power supply, and then we will slowly turn up the voltage. All right, we can see already how quickly the amperage is rising. We are already at 4 amps at almost 7 volts. So this is much more effective than the previous models. As I get up to about 12 volts, which this is the current you could expect to draw, more than 9 amps. We can see already how much gas is being generated. If this seems like it's getting too warm, just ease off on the voltage on the power supply. Now, this is version 1 of my single output electrolysis attempt, and I think this is an awesome design. So this is a stainless steel food container, and the lid of this container, by the nature of the design of the container itself, is already electrically isolated from the lower portion that can hold a volume of liquid. This lid is lined with a piece of plastic, which if you look closely, you can actually see is preventing the 2 sides from coming into contact. What that means is that I can connect one electrode to the lid of this container, have it dipping into the volume of liquid inside, and then use the main body of the container itself as my second electrode. Now, this is how that works out in practice. I still have my stainless steel whisk acting as one of my electrodes, and this is packed full with the stainless steel scouring pad, which once again increases that electrical surface area where it can make contact with the water and produce your hydrogen or oxygen gas. Now, because these 2 layers are electrically separated, we really don't have to do any modifying of the container itself besides drill a hole so that the whisk can pass through. And the way that I attached the whisk permanently in place was to use a little bit of solder, which you can solder stainless steel together, and since my whisk electrodes are also stainless steel, well, it joined to this container no problem. Now, once this container is filled with my electrolyte solution, I just insert the lid into this, screw it in place, and then connect my electrodes. Now, the first electrode I can connect right here. The second one is connected to the container itself just by sticking a piece of conductive metal under it, which I can then connect to my alligator clamp. Now, before running a single output electrolyzer, you have to be very careful not to cause an accidental ignition, which could flash back into this container. Because remember, the gas you're now going to be producing is extremely explosive in and of itself. It will travel down a tube and into the container, so you need a flashback arrestor. Now, what this is a length of tubing that is sticking under the surface of a volume of water, and then another tube at the top, which will be your output. So when gas is injected into this tube, it has to bubble up through the water before it reaches the surface and can be ejected. This means if something ignites the output of this gas, the flame will travel down into this bottle, but instead of continuing through this tube, it will hit the surface of the water, which will prevent the fire from traveling all the way back. If a spark actually occurred inside of this container, it would explode, absolutely. Now, I would hope that if that were the case, the fact that this lid is lined with a plastic sleeve would cause the lid to just blow off, instead of the entire container fracturing something like a grenade. So having a single output electrolysis device is inherently dangerous, but using a bubbler really mitigates the risk. So I will move this over here, so we have room for the bubbler, set this in place, and then I'll turn on the power supply, and you will see that because the electrodes are in such close proximity in this container, once again, we only have one actual whisk electrode in this, while the container itself acts as the second electrode. Well, it's going to work really well, and it will draw a lot of power. So the power supply is turned all the way down, so when I power it up, it will be very low, and I can dial it up incrementally. Already at 2 volts, 2.5 volts, we're drawing 2 amps. That is a lot of power draw compared to what we were drawing on the earlier version. So already you can tell how much more efficient this setup is. That's much less power for a much greater volume of gas. I can see that it is slowly creeping down this tube, and soon you'll see a bubble. Right there. Now that may not seem like much, but at 2.5 volts, that is a ton of gas. Let me turn this up, and we can bring this power supply all the way up to its 10 amp capacity. Look at that, over 10 amps at under 4 volts. Imagine what would happen if you connected this to a 12-volt battery charger, how much current you would be drawing, and how fast you would be producing gas. Now, you probably would burn out your battery charger pretty quick because that would be a lot more power than it was rated for, but you can produce a lot of gas with this setup if you have a power supply that can handle it. Now, I've attached a longer length of tube so that I can bring this down into some soapy water and give you a demonstration, well, of how explosive this gas is. That is more than enough to make a bang. I should have been wearing earplugs for that. Holy smokes. That's not going to come across on camera how loud that was. It's like a gunshot. That was a very tiny volume of gas for a very loud bang, and that is why a setup like this, it's just dangerous. There's no way around it. Combining the output of an electrolysis device, it's dangerous stuff, but you can get extremely good output. Now, a couple more things about this particular design. I've decided that the best way to run this is to connect the positive end of the power supply always to this center electrode, because this connects to the whisk and the stainless steel wool, which is the easiest component to replace. And as we've seen in the earlier models, it's always the positive electrode that does the most corroding. And so if we connect the negative electrode on this device always to the container itself, the container should last basically forever. And if we ever have to replace any components in this, it will always be the very inexpensive stainless steel whisk and steel scouring pad on the inside. So this thing will last basically forever. The final design I have to show you in this video is perhaps the most brilliant implementation of a combined output HHO device that I have ever seen. It may not look like much, but this can compete with the most meticulously crafted precision machine devices that anyone has come up with. And it costs maybe $3, requires only 1 minute to assemble, and consists of a sock, 2 scouring pads, and a couple of wires. This is super clever, and I can't wait to show you how it works. So this is the completed design, and I think the easiest way to show you how this will actually work once we submerge it in some electrolyte is to just build a new one in front of you. So the components that we will need are a couple scouring pads, a small piece of a sock, and a few scrap copper wires, with the ends stripped off. To assemble this design, I'll form the negative electrode on the inside of the sock, first by sticking the stripped end of my copper wire deep inside, and then I will follow it with the scouring pads. Now, I think I'll actually use 2 on the inside of this sock, and then find another scouring pad for the outside, simply because I want to fill this volume on the inside of the sock as much as possible. Now, this wire should be making electrical contact with the pad on the inside, forming our first electrode. Now, a third scouring pad can be taken and unrolled over the outside of the sock. These pads actually unroll quite easily because that's how they're made in manufacturing. They start out in a sock shape, and then they're rolled up into a small little pad. Now, once I have this outer scouring pad fairly evenly stretched out, this gives us a huge amount of surface area surrounding that inner electrode on the inside of the sock. And the 2 sides are separated by only the very thin distance of the sock material itself. This prevents the 2 electrodes from making direct electrical contact, and yet keeps them in very close proximity. The last step is to simply take our second copper wire and insert it under and maybe weave it through this outer electrode. And then we can twist these wires together so that they are secure, and then this thing will be done. All right, so I've got a container of electrolyte here. I am actually risking using potassium hydroxide in this open container for now. I'll just be very careful as I'm filming this segment. And the first thing I'll do is I will connect up my power supply. Theoretically, it says 0 volts right now, but I don't really trust that. I think as soon as I get a load on this, it'll shoot up a little bit. So let's slowly submerge this in, and we'll see how low a voltage it will take to reach the full 10 amp capacity of this power supply. All right, still reading 0 voltage. Let's turn this up. So currently at 4 volts, this is drawing the full 10 amps, which is just about the same performance as this design, which I showed you last, at a fraction of the price and way easier assembly. So this thing, if you are looking for that combined output, this is the way to go. Now, there are some bubbles coming up in this, and it's developing a bit of a foam thanks to that potassium hydroxide, so I can light these bubbles on fire. And you can see that they are explosive, but much less so than the bubbles that we were producing with this. And that is because currently the top of this container is completely open, meaning that the majority of the oxygen is still being formed on the outside of this sock. It's forming on this outer electrode and bubbling up to the outside of the container, while the hydrogen is generally bubbling up in the middle of the sock. This means that the hydrogen and oxygen is still separated by a small distance as long as the top of this container is open. But the moment we've sealed this container and fed the gases into a tube, they would be combining together before they actually reached the end of that tube, and we would have that fully explosive HHO mixture. In this configuration, the bubbles are slightly explosive, simply because that oxygen is still partially mixing with the hydrogen in this configuration. It's just not quite as mixed as it would be after going through all the tubing. Once you realize how this design works, it doesn't take much thought to realize how much more efficient you could make this if you simply scaled it up. If you took something like a knee-high tube sock, stuffed it absolutely full with these stainless steel scouring pads, and then unrolled a few extra on the outside, you would have something that could probably draw, I don't know, 100 amps at maybe 4 or 5 volts, and you would be generating a gallon of gas every 10 seconds. It is an awesome design, and it's so simple to make. Even something as large scale as that would probably only cost you $20. Wow! Well, I hope you enjoyed this video. I know I